Alrighty, so hello and welcome back. I'll keep my voice a little bit lower now because it's getting a little bit later here. Yeah, so hello everybody. Yeah, you know what I'm gonna do? I'm actually gonna start whispering, because what's gonna happen is I'm actually going to I'm gonna start whispering because I'm gonna start whispering, and the reason is because if I continue, right, as things are, if I continue as things are, what's going to happen is, hopefully it's not too loud. Actually, I don't know. Hold on. Is that too loud? Maybe that's too. That might be too loud. Yeah. Hold on. Let me see. Testing. Hello. So the problem that I'm gonna run into is, even though I'm whispering, it seems really loud. Hold on. I don't want it to be too loud. I want it to be louder, but not that loud. Okay, how's this? Testing. How is this? Is this loud enough? Is this too loud? I'm not sure. I'm trying to make sure if it's not too loud. Okay. I just remember these settings here. So the reason why I'm doing it this way and starting to whisper now is that if I don't start whispering now, as time progresses, we're going to hit this point where people are going to sleep, and I'm still going to be talking loudly, and I'm going to have to switch to whispering. So I'll whisper now, so we don't have to do that, hours from now. Anyway, okay, so today we're going to look at, now we're going to look at the next question, and another programming problem. Yeah, we'll just do that. Took a small break, got kind of hung out for a bit, watched, ate some food, made some food. Didn't finish all of it, but I was watching some other folks' videos talking about their lives, and I have to be blunt, it makes me feel a lot better about myself. Like, I'm so far from perfect. Like, I need God, I need God. Oh, here we go. Let's see. Hopefully I can get to this tweet. Thank you, Feta, for this. Hopefully I can see it. Let me see. I deleted my Twitter account because I don't like Twitter. Okay, hold on. Thank you for finding that tweet. I noticed you deleted it. Yeah, I don't really like Twitter. I'm trying to, eventually I want to delete my YouTube as well, but I don't know. I mean, I'm not really ready yet to do that, I guess. I want to have another platform to upload and stream from before I delete YouTube. I've been streaming for a long time. It feels weird to not stream anymore. But anyway, so what I was getting at is, I forgot what I was even saying. Oh yeah, I was watching someone else talk about their life, and my life's not perfect, but I'm blessed to be beyond what I deserve. I'm extremely lucky, I'll say. I'm extremely lucky, and yeah, I should say that. But watching other people talk about their lives being extremely difficult does make me feel better, because I'm just grateful that I'm not struggling that much. That I feel like that, and I don't feel like that at all. I feel very good about my life. I mean, there are things that drive me crazy, but ultimately, I trust God, trust Jesus, and he'll sort of guide me, set me straight. Channeling Ted K. What is Ted K? What is that? Oh yeah, so let's take a quick look. Everything is like this now. Tear down something imperfect but load-bearing. Realize it was load-bearing. Watch it spontaneously reemerge as a matter of cold practicality with none of the things that made it beautiful. Isn't this just marriage? What is this a reference to? Are you talking about this was about with pimps and prostitutes? Or I forget what this is about, but I forgot what we were talking about when you said there's a good tweet about this. I don't know, this seems a little too like abstract for me to really get a hold on. I don't know. I mean, people destroy things they shouldn't destroy all the time. That I can understand. And I realized they needed that thing. It's actually pretty normal behavior, but that's probably as far as I can. It's about marriage. Oh, ouch. Yeah, I have very uncomfortable thoughts about marriage to begin with, but that in particular is, yeah, it's not something you want to destroy. You can't really fix marriage once you've destroyed it. There's some things you can destroy and you can rebuild it. You know, if you destroy a car, you can get a new car. But marriage is like that, where once it's destroyed, it's kind of gone. Actually, cars are maybe not a good example, because cars, you really can't rebuild them usually. It's usually not worth the expense to rebuild it. You just get a new one, and that's, in my opinion, that seems to be how it is with marriage. Is if you cheat on your wife or husband, then that's it. You know, that's a wrap. That's a wrap. There's really no fixing it. Tweets and quotes give more context. Yeah, interesting. Well, thanks for finding that. I appreciate that. I'm not gonna go too far into it, but I'm like, I almost don't want to think about destroying marriage. You know, it's like it's not fun to think about. There's a lot to talk about there too, but maybe not now. Don't complicate life. Life is very easy. I wouldn't say that. I wouldn't say that. No, I wouldn't say that. I would say life is simple. I wouldn't say it's easy. Definitely not easy. No, and the Bible says, it doesn't say if tribulations come, it says when. So your life is not going to be fun, you know, not going to be without tribulation. But following what the Bible says is pretty simple overall. You know, you need Jesus. You need God. Okay. Write a program to find the nth ugly number. Ugly numbers are positive numbers whose prime factors only include 2, 3, and 5. Example, n equals 10, output 12, 1, 2, 3, 4, 5, 6, 8, 9, 10, and 12 is the sequence of the first 10 ugly numbers. So this is a relatively easy question. Or should be relatively easy. Basically, you have prime factors 2, 3, and 5, and numbers that only include prime factors 2, 3, and 5 can be written as the product of 2 raised, we'll call it alpha sub 1, 3 raised to alpha sub 2, and 5 raised to alpha sub 3, where alpha sub 1, alpha sub 2, and alpha sub 3 are just integers that are greater than or equal to 0. And obviously, now the tricky thing here, this isn't very easy, the tricky thing here is, so in order to increment to the next ugly number, you basically increment that tuple of alpha sub 1, alpha sub 2, alpha sub 3, increment one of those values. And the tricky thing here though is the order of these numbers is not necessarily obvious. I guess this is what makes this interesting. 1 is typically treated as an ugly number and does not exceed 1690. Yeah, so the order matters a lot, right? Because depending on what value you give this integer, it's not, it's not obvious which. It's actually not even necessarily just incrementing this alpha sub 1 or alpha sub 2 or alpha sub 3 to get the next value. It actually could be incrementing a previous value. So this is a pretty interesting question. Yeah, definitely very interesting. So how do we find, excuse me, the question really is, yeah. Given some x equals 2 to the raise the alpha I, 3 raise the alpha 1, alpha 2, and 5 raise the alpha 3, what's the next largest value of this form? And I don't think it's obvious, actually. I don't think this is an obvious question. This might be actually a much harder question than I'm letting on. Knowledge makes it easy. True. Knowledge helps a lot. Wisdom. Praying to God for wisdom. That seems to be the thing that makes things the easiest. The Bible says it, that God will give you your heart's desires if you obey Him. You pray to Him and you ask Him for it. However, it's the temptation to sin is incredibly strong and damaging, and that usually never get there. Most people never get there. The vast majority of people never get there. So the question is, if alpha sub 1, alpha sub 2, alpha sub 3, I want to find the next value of this form. So let's go through some examples, because I don't think the formula is going to be easy. So 1 through 12, right? So you have 1 to the 0th, 2 to the 1st, 3 to the 1st, 5 to the 1st, 2 to the 1st, 3 to the 1st, 4 is 2 squared. 1, 2, 3, 4, 5, 6, 4, 5 the first. I don't know. I'm sorry, I did this wrong. Okay. So that's 6. 8, I think, comes next. 9. 10. 11, 12. Yeah, see, this is quite the formula we got going on here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the problem, you see, is from all zeros, you want to increment 1 first, but you'd want to decrement this 2 to go to 3, and then decrement this 3 and increment by 2. So you divide by 3, multiply by 4. Then you would divide by 4, multiply by 5. Then you would divide by 5, multiply by 6. Then you would divide by 6 and multiply by 8. Divide by 8, multiply by 9. Divide by 9, multiply by 10. Divide by 10 and multiply by 12. Which, hopefully there's some patterns in here that we can make use of, some rules. So, where you see a 2, you want to divide by 2, multiply by 3. In some cases. But not all of them. You see a 2 squared, you multiply, yeah, I don't know, man. This may not be so simple. Or you see a 10, you want to divide by 10 and multiply by 12. Would these be enough rules? So with these rules, how far can we go out? Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n equals 10. Let's say if we can go to n equals 15, how far would we go? So we can continue to 13, 14, 15, 16. Alright, this is 11, 12, right, because 13 is not, 14 is not, 15 is 16, 17 is not, 18, there's a couple ways to do this actually. There are a few ways, but 18 is 9 times 2 is one of them. 19 is not, 20 is 1, right? It's 2 times 10. And 21 is not, 22 is not, 23 is not, 24 is, right? 6 by 4, both of which are. So you could probably find these numbers directly. So if one thing to note here is if we're talking n doesn't exceed 16,090, I want to say that that's not too bad. I could be wrong. Excuse me, but what I want to say is, because the check to see if a number is a quote-unquote ugly number is logarithmic time, right? You can, in terms of the number, the size of the number, because you could just divide by 2, 3, and 5 as many times as you need. And actually, you can even do it faster than that. You can do using Legonder's formula. Generate the value 2 raised to the alpha sub 1 times 3 raised to alpha sub 2 times 5 raised to alpha sub 3, and then, or even better than that, can you do it better than that? I guess you'd want to use doubles at that point, but basically you can divide out those factors from the number to find out, oh no, I'm sorry, not Legonder's. No, Legonder doesn't work here. I'm sorry, I take that back. Totally wrong about that. That only works for factorials. Sorry, so you just divide by 2 a bunch of times, divide by 3 a bunch of times, divide by 5 a bunch of times, and if you get 1, then that means it's an ugly number, quote-unquote ugly number, and that should be logarithmic time. Then so, depending on how big these numbers are now, the reason why I'm not so sure about this is because I think this sequence grows in value exponentially, in which case I don't think you'd be able to do it that way. And I'm tempted to test that. But that's like a simple brute force approach, which we might want to make use of. If the rest of division by 2, 3, and 5 are not equal to 0, then they are good. If the rest of division by 2, 3, and 5 are not equal to 0, then they are good. I'm not sure I understand. I think you may need to explain a little bit more for me, if you don't mind. Okay. So what I'm looking for, though, is maybe a pattern to generate the sequence in a more direct way, rather than testing the numbers to see if they have this property, because I suspect that the numbers are really big, and we'd have to go through a lot of numbers to test them. I could be wrong about that, though. I mean, this could be a lot easier than I'm making it out to be. So these numbers, you get 3 to the 5th. Now basically what I want to do is see if I could have predicted this somehow. There is another approach too that uses divide and conquer. Well, maybe that's what you're describing. Basically, yeah, if you divide, not divide and conquer, dynamic programming, where, yeah, you divide by 2, 3, and 5, and if all of those numbers are, actually, if any of those numbers, really, if you have to have at least 2, 3, or 5, it's divisible by at least 2, 3, or 5, and each of those numbers are have to be ugly numbers. Oh yeah, we could just do it that way. That's a lot easier. That's a lot easier. That's faster than logarithmic. But no. That's easier. However, the problem with that, you know what we can do? No. That's easier, because there's only 1,690 of these that we're paying attention to. That's easier than dividing by 2s and 3s and 5s, but the problem remains that this could be a very large number. Yeah, these could be exponential, the number of numbers they have to work with. Right, yeah, you could divide by 2, divide by 3, divide by 5. If any of those, if it's divisible by any of those, it has to be divisible by at least 1, and if any of them are, it's divisible by that, and that number by induction, by dynamic programming, is already shown to be an ugly number, then you're in good shape. In fact, it has to be, yeah, if any of them work, then you're fine. Then that number itself is an ugly number. And then, but the problem is that if there's an exponential number of these, then you run into some issues. You run into time limit problems. I mean, we could just test it. You know, we could just write that code and test it if we want. I might do that now. Try to solve it directly, and then go to and then see if there's a faster approach. Different, not equal. Interesting. Let's see. Okay, let's do it this way. I think an ordered set is what we want. Yeah. Oh, we're gonna count. I'll find the nth. It's not gonna. We're not gonna. Yeah. Okay. So for int, really, it's a while loop. While. Then we're gonna say. It's actually more like. I'm actually not sure how we want to do this. So I'll start with I equals 1. Really, you can do start with I equals 2, a while loop, increment I. You're going to say if I modulo 2 equals 0, and so you have 3 different checks. We'll do. And right, these should be equal to 0 to show the divisible by 2, 3, and 5. So if and only if check 1 and check 2 and check 3, then we're going to insert I. And now we say you really can do just say true. This is an unordered set, so we'll just say if return -1 here. If ugly numbers dot size is equal to n, then return I. Yeah, something like this. Let's see what happens here. Does this compile? Time limit exceeded. Nice. Oh, I'm sorry. That's why. Wrong answer. 13 expected 12. That's my mistake. Okay. Let's do, I don't know, some random numbers. Let's just do that, see what happens here. How long does it take to do this? Yeah, okay, I thought that might happen. So we go to 100, and I think it's exponential. 1536. Okay. 200. So this is like a brute force, a dynamic programming approach, somewhat brute force. Let's just do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Just to make sure we have those correct. Those have the right idea for those. Invalid compile test case. And I think it's got to be a positive number n. Wrong. Output 2, expected 1, input 1. Yeah, I mean, just call this an edge case. Yeah, I kind of wasn't sure. I was like, that's not really that important. Okay. So when you get to 400, like I said, I think this is exponential. I think that's why this won't work. Output the first number that's not divisible by 2, 3, and 5. The first number that is not divisible by 2, 3, and 5. Now, what do you mean? What do you mean by that? I don't think that's the right answer. As described. No offense. I think you might want to rethink that. Alright, there we go. Now it's at 800. 660 milliseconds. Let's go to 1,000. We don't time out at 1,000. No, we do. We time out at 1,000. Yeah. So, interesting. So we might want to think about these production rules then. So that's the brute force approach. Like I said, I don't think the brute force approach is going to be fast enough because it seems that these numbers grow exponentially with n, with regard to n. But we do seem to have some kind of a pattern, which is interesting. Let's see. So let's do 10, 15, and 20, and let's print those values. So something brute force that we can work with here. Just call it T. I would just call it V rather. Sort these. And then we're going to output these. Let's see what we get. Let's get a TLE. Forgot. We don't need that many anymore. We just need like 10, 15, 20, 25. Really the numbers we need. Factor by 2, 3, and 5. That means 2. You missed one. 2, 3, 4, 5, 6. You got 8, 8 again twice there. I mean, you want course. What you want is this list, right? 1, 2, 3, 4, 5, 6, 8, 9, 10, 12. But yeah, I don't know what you mean, man. I don't know what you mean. So basically, yeah. So basically, we can use this data to test the numbers. Obviously, we got this one correct, where we did that by hand. 16, 18, 20, 24. Yeah. So okay. The production rules basically go like this. You see a 1, you go to 2. From 2, you go to 3. You divide by 2, multiply by 3. 3, divide by 3, multiply by 4. 4, divide by 4, multiply by 5. 5, divide by 5, multiply by 6. 6, divide by 6, multiply by 8. 8, divide by 8, multiply by 9. 9, divide by 9, multiply by 10. 10, divide by 10, multiply by 12. Now, when you saw 5, you divided by 5, multiplied by 6. So here's a repeat. 5 multiplied by 6 is repeated. 5 multiplied by 6 is repeated. Okay. Divide by 2 and multiply by 3. Basically, I want to come up with some rules and some precedents on those rules, and that should, in theory, be able to be enough for us to find out how to go from point to point. So you go color code these rules. So 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 8. That's kind of a tricky one. Now that one is interesting because it's not really 6 to 8, is it? That is 3 to 4, right? That's 3 to 4. I'm just kind of guessing that I think these rules, that we can do it this way, that it'll work. Because 3 goes to 4, right? So this is 3 to 4. Takes us from 6 to 8, right? 8 to 9 is kind of its own rule. 8 to 9, and then 9 to 10 is also its own rule. But here we see this 5 to 6. And then, okay, let's see if any of these rules apply before we continue. So 2 squared, we see 4 to 5, we see 6, could be, we see 3, could be 3 to 4. The order, yeah, what do they call that? There is an ordering on these rules, like the rules that come in that you see first are the ones that have higher precedence. So we see 2 to 3. That should happen before. No, I'm sorry. It's the other way around. The lowest precedence are the rules that you want to use. They're the ones that come down. The most recent rules are the ones that you want to use first, and the reason for that is that you have the smallest difference in your number. So if you think about divide by 2 and multiply by 3, that's multiplying by a factor of 1.5. Divided by 3 multiplied by 4 is a factor of 1.3 repeating, right? That's smaller than 1.5. So you actually want to use the rules that come further down first, if you can. They take higher precedence because you want your numbers to be as close together as possible. So that means we would look for, I don't see 3, I don't see 3 squared there, I don't see 2 cubed there. I do see a 3, but maybe I don't see a 5, and I do see a 2 squared, so it looks like this blue one is the one we want to use. So 2 squared becomes 5, so this would go to 15, which is what it does, I believe. Right? I have 3 and 5. So you see, so these rules are, what are these rules? In order of precedence. This green one, this purple one is 3 squared to 10. 2 cubed to 3 squared. And we'll color code everything, why not? There's a bunch of these different rules. I don't know if I can do this all with just rules. I don't know if that works. But we can look. 2 cubed to 3 squared. So then you have this green one is 5 to 6. This blue one is 4 to 5. This orange one is 3 to 4. To move my mouse a little bit here. And then what comes next? This red one, 2 to 3. So from 3, 5, you have 5 to 2, 3. So 3, 5 would give, and then 5, 3, and so 3, 5 would be 3 times 6 is 18. So 18 should be next, which is not what we get. We get this 3, 5 to 16. That's interesting. I don't think any of these rules give us that. Gives us a new one. Yeah, the ones that are right next to each other are almost, no, not right now, no, I shouldn't say that. Anything with 3 is 2 squared, 5 is 2, 3, so you would get like 2 cubed times 3, not 16, so this is sort of another one. That's sort of a new one. Not obvious at all. Then from 2 to the 4th, what do we get? The highest precedence for 16. 2 cubed gives us 3 squared. Probably that one, 3 squared times 2, which is exactly what happens. So 3 squared times 2, or 2 cubed, yeah, 2 cubed is 3 squared, yeah, so this gray one. And then 2 and 3 squared, we want to go to 2 and 3 squared would be probably 2 and 10 to 20. So 2 squared and 5. Yep, that's where it goes. It's just kind of purplish. And then 2 squared 5 looks like, well, we have a 5 here. Don't have a 2 squared 5, we have a 5. So 2 squared 5 should go to 2 squared times 6, which is 2 cubed 3, which is exactly what we get. It's that green one again. So it looks like we could have limited success using sort of production rule type of hopping around here. If it starts in n for I equals n dot 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 dot, starts in n. Yeah. Well, it actually starts. It's the other way. It's the other way around. It's the nth number in the sequence they're looking for. So if they're looking for n equals 15, they're looking for this number 24. Right? That's the 15th number. So I'm trying to come up with rules to generate these numbers. Now the tricky thing is there may be numbers that exist that aren't handled by these rules. That's kind of what we want to test to see if there's any cases that we're missing. And we can actually generate these rules on the fly. So what you would do is you can have the ugly number set, and that sort of that approach that you see, that's, you know, each time you add another ugly number, you get ugly number that's set. If you want to do a linear search, you can do that linear search to find out if you've discovered any new ugly numbers. Probably what you'd want to do is now the space between each ugly number is exponential. That's sort of I guess the problem that I'm seeing. And the tricky thing is that you can't use this iterative approach, linear search between those spaces because they get to be too big. Now the thing is, I'm not sure that this covers all of the rules that we might need, right? So if we generate, so n equals 20, I'm not sure that, I'm not sure that, so this would be n equals 20. I'm not sure that these rules cover enough. And I'm not sure if we need to generate more rules as we go, and maybe we should use an iterative approach to generate those rules. I don't actually know. These questions I don't have the answers to. Alright, so 24 is 2 cubed times 3. Now if we use our rules, 2 cubed gives us 3 squared, so we should go to 3 cubed, which skips 25 and goes right to 27, which is not correct. It actually, we have a new rule. It seems like when you're going from, one to the next, there's this kind of jump that produces a new rule, which I guess is kind of interesting. So 2 cubed times 3 is another one, which is 2 cubed times 3 goes to 25. And really these rules are based around these kind of, not pain points, but these different points where the ugly numbers are right next to each other. So it's now 25 to 27, 5 squared. Well, we see 5 twice. I mean, 6 times 6, no. That's not correct. It looks like this is another one. This just goes 5 squared straight to 3 cubed. You know what you could say, actually? These are themselves ugly numbers, 5 squared and 3 cubed. And you could say something like, I want to say something like, if you have a sorted list of ugly numbers, no, that's the thing. It's like there's sort of like 3 dimensions that you're working on here, and these numbers, they kind of interact with each other in such a way where they rest. Sort of, if you multiply by 5, but you multiply the other ones by, these are zeros, but this 5 is a certain number of values. I want to say there's like some interplay between, like, if you think of these as like almost like unit vectors in certain directions, there's like some interplay that happens where you can relate these to each other. I don't know what I'm trying to describe here. Like, generating 1700 numbers is not the hardest thing to do, and then sorting them is sort of fine. It's just, it's not obvious how many numbers you need to generate to get the nth number, if that makes sense, because of the way these things kind of operate. That's kind of what I'm hung up on, stuck on. So that 3 cubed to 30, what is that? So 3 cubed, the rules we see a 3 squared here. That should give us 2 times 5 times 3, which is 30. So we use that one. There. And then to go to 32, so we have 2 times 3 times 5. Like, this is sort of the 1, 1, 1 tuple. But look how many numbers we have before we even get to that 1, 1, 1 tuple. There's so many. There's so many other ones in between. Actually, maybe, I don't know. Maybe these are all the rules you need. Once you get to this 1, 1, 1 tuple, you're sort of at like a baseline again. And then you have all the rules after that. Oh, I want to say something like that. I really don't know. Let's get to 2, 3, 5 now. 2, 3, 5, you have 3, 5, it looks like. So that's 2 to the 4th times 2, which is 32. Yeah, that's exactly what it is. And then from 2 to the 6th, you have 3 to the 4th, which is interesting. How do we get to 36? From 2 to the 5th. Oh, here you go. Yeah, 2 to the 5th, you would take this one. You'd have 4 times 3 squared, which is exactly 36. I think these are all the rules that you need from here. I think this is it. And the reason is that you got to this point, this 1, 1, 1. Those are sort of all the different transformations you need to go from 0, 0, 0 to 1, 1, 1. So now you can go from 1, 1, 1 to 2, 2, 2 to 3, 3, 3 to 4, 4, 4, etc. You know, ad infinitum. I think that's sufficient. I think that's all you need. That's probably it. It's probably all the transformations you need. As weird as that seems, that's my guess. So now if we go to, okay, 36 now, what are the next set of problems, set of questions? Or a set of values. So we got to 36. So now 36 is 2 squared times 3 squared. Now I want to go to the next one. So 2 squared, 3 squared, we would take probably just 3 squared. So 2 to the 5th. 2 times 5 times 2 squared, which is 2 to the 3rd times 5. Which is the next value. And then 2 cubed times 5, we see 2 cubed times 3, 5 squared, just 2 cubed. We'll go to 3 squared. So 8 becomes 9, so now you have 9 times 5, which is what was correct. Then, so 3 squared times 5, looks like this one, so now you have 2 to the 4th times 3. And, which looks right. 2 to the 4th times 3, now we get to probably this one, which is 2 to the 4th times 3 is, this is subsumed by 2 cubed times 3. So 2 to the 4th times 3 times, so this is basically 5 squared times 2, which is exactly what we're looking at. And then 2 times 5 squared, so 5 squared we say goes to 3 cubed, so 2 times 3 cubed, which is exactly what we're looking at. Very interesting. Super interesting. So my thinking is that this is probably enough for the rules because we got to this point here. And I think all of these rules will generate now from here on in. So now we just need to encode these rules, and that's it. So let's do like sort of a next function. See if this works, and we'll run a test. So we'll call this auto brute force or slower. we're actually going to run a test against these. To verify. So slower of n. Okay. And now we want the actual algorithm, which is going to be, we also don't need to print these anymore. The actual algorithm, we're going to have this next. Some value. Actually, we're going to have a tuple. I'm going to call this alpha. It's alpha tuple here. And we're going to get the next tuple. So we'll say const auto ABC equals alpha, and we're going to say we have a big if-else set of blocks that we're going to go through. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9 of these rules. So if we have A is 5, it's if C is greater than or equal to 2, then we're going to return standard make tuple of ABC. It's going to be C minus 2 and B plus 3. Else if A is greater than or equal to 3 and B is greater than or equal to 1, B is greater than or equal to 1 and C is greater than or equal to B is greater than or equal to so that's this one. B is greater than or equal to 1 and C is greater than or equal to 1. And it's going to be, I'm sorry. Wait. No. It's A is greater than or equal to 3 and B is greater than or equal to 1. And you're going to say A minus 3 and B minus 1 and C plus 2. And this is how we're going to encode the rules. Now you could in theory write a routine to actually automatically encode these rules, but we're not going to do that. We're going to just do it manually. So now we have A is 1, or B is 1, C is 5, and then, I don't know, I'm sorry. Yeah. B is 1, C is 5, A is plus 4. And these are subtract 1, subtract 5. Did I get that right? No, it's 1, I'm sorry. My brain, man. And the next one is here. It's very error prone. 3 squared is 2, 5, so 3 is B, and 2, 5 is 2, 1, and 5, 1. A, 1, and 5, 1. Minus 2. So B minus 2, and then A plus 1, C plus 1. And then A minus 3 to B plus 2. A minus 3 to B plus 2. And C is left alone. Five is 1, so C is 1, and A and B are plus 1. So C is greater than or equal to 1, then A or B are plus 1. C minus 1. I'm probably doing this wrong too. Hold on, let me just make sure I got it right. So 5 squared. So these things we remove. Minus 3, minus 1, minus 1, minus 1, minus 3. Oh yes, he doesn't get touched. That's true. That's C greater than or equal to 1. I got this one. A greater than or equal to 2. We're going to lose A, 2 A's. Excuse me. And we're going to add 1 C. Now I could be totally wrong if these are all the rules though. There could be more and more that get generated as you go. In which case I'll be sad. And now this is 3 to 4, which is B. B greater than or equal to 1. I'll lose 1 here. And add 2 here. And then finally, the first rule, the simplest one. A greater than or equal to 1. And B plus 1. Alright. Let's see how we do here with this. See how we do here with this. How far we get. So this tuple. Okay. Otherwise, we'll return the same thing, I guess. And we could say for int I equals 0 less than n, we're going to say standard tuple x equals 0, 0, 0. X equals next of x. And then we say did we do here? How did we do here? One, two, three, four. I guess in every, we don't know what to do, we'll just multiply by 2. Oh, what? 16, 36, 72, 144. No. No. Oh. It's close. It's real close. Huh. I don't know, man. It's not correct, though. To get all the rules. 1, 2, 3, 4, 5, 6, 7, 8. How many got over here? 1, 2, 3, 4, 5, 6, 7, 8, and 9. I missed one. I gotta fix that. But I think, oh, my back. Oh, ouch. Excuse me. I forgot what I was even going to say here, thinking. My back hurts, that's all. Back aches. When n equals 1, this is initially the first value. So n should really, I should start off at 1. And when n is 1, you don't even iterate. When n is 2, you go to the next one. Alright, you update the next. Yeah, so this should be fine. This should give us the right answer. Guess it's 15 though. So we're missing one hop in between. Which one are we missing? 5 squared? When c is greater than equal to 2, b is greater than equal to 3, a is greater than equal to 3, b is greater than equal to 1, b is greater than equal to 1, c is greater than equal to 1, b is greater than equal to 2, oh, I missed that one. When b is greater than equal to 2. Yeah. You have a and c plus 1. When b is greater than equal to 2. Yeah. Okay, let's try again. We go again. Oh, there we go. Yep. That's exactly correct. That's exactly what we're expecting. Alright, now what? Nice. So let's put a bunch more in here. Let's go. How do we do? Oh. Really? Okay. Interesting. So we're right up to 50. Let's go to 100. What happens for 100? Oh no. Wait, what? No. Sorry, we're wrong. What does this give us? Wrong answer. Okay, where do we start making mistakes? 75, 76. Where is that exactly? This is where we have problems. This is it. This is where we have problems. So 75 goes to 80. This is just 3 times 5 squared, right? Now the question is, this goes to 80. Now what do we do? Yeah, this go to 3. It's 5 squared, we'll go to 3 cubed, right? It's 81. But apparently it goes to 80. Which is really just 4 times 5 squared. Imagine that. Dividing by 25 and multiplying by 27. Times 3 times 5 squared is less than is less than multiplying by 4 times 3. It's 3 times 5 squared. Would you believe that? Would you believe that? This... No, I'm sorry. This is 15 to 16. Take that back. Am I crazy? Am I nuts? Am I nuts? This is 81. Over 15, 27 over 25. No kidding. Actually, 16 over 15 is more desirable. Uh-oh. Uh-oh. That gives you 80. Huh. No kidding. I have that one. That one's here. Huh. Huh. Interesting. Interesting. This is the wrong order. This is... Well, you can figure this out, right? 27 over 25. 1.08. These need to be ordered by these ratios. 2 cubed is 8. 8 times 3, 24. 25 over 24 is 1.0416 repeating. Fifteen over 6, 16 over 15. 1.06 repeating. Ten over 9. 1.1 repeating. So this actually belongs here, between these two. 9 over 8. 1.125. 6 over 5. 5 over 4. 4 over 3. 3 over 2. Okay, we're fine. It's just that was in the wrong spot. So, wrong precedence here. Very interesting. That belongs between B1 and B2, right? B1, B2. There should be this guy. Between B1 and B2 is this guy. B1 and B2. There is C2. And wow. No kidding. Alright, how do we do now? Ah, now we're correct. Okay. For, you know, some of that. Let's try this now. Wrong. Oh, come on, man. Really? It's upsetting. Somehow I knew this probably wasn't going to work. This approach. Oh, immediately. 36. Immediately afterwards. Should be 108. We got 120. Now, how did that happen? 80 to 108, 80 to 120, 120. Okay. All right, this is 2 times 40, 2 times 20, or 16 times 5, really. And 120 is it's 10 times 12, 2 times 5, is 2 squared times 3, 2 cubed times 3, 15 times 8, yeah, okay. And this is 2 times 54, 2 times 27, which is it's 3 cubed. 27 times 4, yeah, 3 cubed is 27. Right. 80 plus 4 times 7, yeah, okay, so, great. Wunderbar. 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 Another question is, how did we end up going from here to here? How did this happen? How did this happen? 2 raised to the 4th times 5, 2 squared times 3 cubed. Oh boy. There's another approach to this question that I'm going to go for. It's another kind of brute force problem approach. It's not great, but it should do the trick. Alright. 80 by 108. So I'll show you. It's pretty simple, but it's not good, but it's simple. To the 4th times 5 gets us to 2 squared times 3 squared, 3 cubed, which is really minus 2 here, minus 5, just 20, to, looks like 3 cubed, 2 squared times 5, so this is 20 to 27. Is that what I'm looking at here? Is that what I'm looking at here? Yep. Yep. That's exactly what we're looking at. I don't see that rule in my rule book here. That's a big one. That's a big one. That's a new one. Skipped one. We got 120 and 125, but we didn't get 125 to 128. Skipped another one. 35 to 145. 144. That's kind of interesting. 150 and 160 shouldn't be. Well, no, what, how come, yeah, what happened to 150 and 160? Are those just gone? What happened here? Hold on, what? Is this not right either? Uh-oh, uh-oh. But yeah, 75 is here. What is going on? Wait a second. What's going on here? What is going on here? What? Wait a second, what? Wait a minute. Whoa, 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 whoa. What? What do you mean? This is goes from 144 to 243. What about 150? Huh? Is 150 not an ugly number? That's definitely an ugly number. Does that come later? When is it 150? What is going on? Well, that's bizarre. How does that happen? What in the Sam Hill is going on here? How does that go from 144 to 243? How did that happen? Oh, that is so confusing. Oh, I know why. Oh, I'm sorry. No, I know why. Because we jumped at the end. That's my mistake. I'm not thinking straight. Yeah, that's my mistake. Let's try that again. There we go. Okay, I was like, wait a minute, what is going on here? 160 to 162. I'm missing a whole bunch here, huh? Yeah, that's interesting. There's a bunch of these in between. Alright. Using these rules is a little awkward. I don't really know how I feel about it. Maybe not. Maybe not. You could write a routine that generates these rules, but I don't think it's really, I don't think it's really that good. And basically what you would do is you'd have some like, you have like some kind of a mapping, and you know, you'd have sort of a rule that you add to that mapping, and you go through all the rules in the mapping, and you have, you know, some conditions that gotta be met, you know, some values for A, B, and C, and then you have like what happens, you know, the difference depending on which rule, and each rule would have some precedence, you know, some order, and you would use a linear search to define the next rule or rules, to find out if there's something in between. So if a rule doesn't apply, now a rule could apply directly there, however it may be the case that there's another rule to uncover. So you'd want to take a look at some of the numbers in between to see if there's any rules in between, and then, you know, return that value, return the new rule, you know, add the new rule. Yeah, ultimately I'm not really sure how to do this. I'm not really sure. I don't know about all that. That seems kind of awkward, that whole program. What I could do instead, let's get rid of all this. Just do something real simple. We'll just say 25, I don't know. It's -1. Excuse me. We want to say excuse me. If it fits an integer, push it in there. And then we're going to sort what's left over there. And then we're going to return and see how we do. Yeah, very quickly we go. Get out of here. Something like this. Runtime error, buffer overflow. Just overflow everything. Okay. Yeah, very quickly overflow. What is going on here? What is happening? What's going on? What? Given the rainbows and frame my soul to get lost in a rocket roll and drift away. I gotta stop singing that. Stop singing. This stuff is it's not for Christians. I don't know what I did wrong. Did something questionable here. So what did I do? What did I do? What in tarnation? Oh, that's why. No kidding. Brother. Come on. Come on, man. No kidding. Okay, that's probably had something to do with it. I think I see the problem now. Right, I don't have enough numbers. Let's do like 3. Let's do it this way. Oh, I get lost in your rock and roll. No, I don't want to get lost in anybody's rock and roll, man. No, thank you. Well, this is better. Not quite what we're looking for, but better. So I was looking for like 150 and 30, right? Something like this. Let's give that a shot. See how that goes. Should be interesting. Take a little while. Really? Huh? it's still off. Well, excuse me. Well, excuse me. It's close. Huh. Oh, yeah, I see the problem. Gotcha. I think I see the problem. There we go. This is more what we're after. Okay, now let's crank it up a notch. See how we do here. Crank it up a couple notches. Oh yeah, okay, got him. Nice. See if we hit 1,000, see how it works. Time limit exceeded. Okay. Okay, well, pretty good. Now, let's not run this guy. And we'll just... I don't really need this at all. How do we do? Huh. Okay. 1600. Let's go. Let's do this. Seems to be correct. Very interesting. 1690. Now we got it. Well, that's good. And I think this should give me an invalid test case. Nice. Invalid test case cannot be represented in type int. Okay. So yeah, well, that's a pretty easy question, huh? Well, that's easy. That's not bad at all. Seems like we're in good shape. I guess my question is, like, we shave these down a little bit, like 50, 25, 15, you know, something like that. See if we can get that going. Yeah, that's a lot faster, huh? That's pretty quick. It's pretty quick. What we can do, what did I say, 50, 25, and 15? Brother, this is it's a little ridiculous. Okay. Actually, gonna move this outside here. Oh no. No, that should be fine. No. So this is actually a pretty easy question, huh? This is a pretty easy question, huh? Okay. So we're going to just do a straight brute force test. All the numbers. Just cause I'm ugly number set. I'm having a fun time with this question, man. It's an interesting question. As you can see. As you can tell. Time limit exceeded. I don't actually know. Okay. Wanna get lost in your rock and roll and drift away. Give me the meatballs and free my soul. Wanna get lost in your rock and roll. And oh, I should have stopped singing that. I gotta stop singing that. Yeah. Yeah. Does this work? Something like this. Maybe I'll make it 1,000, make it like 100. Give me meatballs. Oh, no. Stop singing that. Just, excuse me, thinking. I get the wrong answers, right? I think we just, yeah, okay. Something like this. What is going on, man? What's going on? I1, J2, I2, okay. all just a little off. Wait, what? J is 2. Starts off with 2. Why does it start off with 2? Should not start off at 2. This should. What? Yeah, what is going on here? 0 should just be 1, right? This should just be 1. This should. J should not be 2. J should be 1. Why is J 2? Why is that happening? So confused. What? That's not. Yeah. That's a 1. Oh, that's why. Okay, I understand. Got it. Got it. That's not the problem. The problem is the second number. Actually, this guy's got to be bumped ahead. I think I understand. Just call it V, I don't know. What? What is going on here? Oh, yeah. Okay, that's what we wanted. Alright, wanted everything to match. Want everything to match. Okay, now if we go to 500. There we go. Okay, looks like we got it. Alright, good. Now if we go to 1,000. So pretty much I just wanted to brute force these values, these numbers, to make sure everything is correct. Everything matches. Time limit exceeded. Alright. What if you do 1,600? What if you do 1,690? And then you throw a little nice hello world out there. Shout at the world. Oh, please close that. Don't need that. I don't gonna get anything at this standard out. Alright, anyway, I think we're fine. I think we got it. I think we can get rid of all this junk. I just like to brute force things. Just to make sure they're correct. But you run into time limit issues, I guess, which is sort of the reason why. Which I guess is kind of the reason why you can't test that through this console. 12 milliseconds, huh? Wow. Can I make that faster? Let's try it. 25, 12, and 7. How's that go? How's that go? 0. Okay, we don't make it. 35, 20, and 10. Let's go a little higher. Not quite. Nope, nope, nope. Closer. About 35, 25, and 15. How about that? Oh, that's enough. That gets everything. Yeah, no kidding. What if we go? We go lower here. Can test our bounds. No, we need 35. It looks like. All right, that should be enough. What did we say we did? 50, 35, and 25, right? That was plenty. The thing is, it's possible for there to be like intermediate values where it's not correct. I don't know. We'll just go for it. We'll just go for it. Maybe increase the bounds a little bit. Just add an extra 10 just for good measure. Time limit exceeded. No, really? Come on. What? What? Alright, what numbers do we have before? What is this? What is this absolute tomfoolery? It's absolute nonsense. Come on. There we go, okay. 328 milliseconds, huh? So we got there. Yeah, this is, this is a little ridiculous, this question. It's a little ridiculous. It's kind of absurd. How far did I go? I was able to like shave it down some, right? Go 20, 10, go 15, 15, 15. How about that? How about that? Doesn't quite make it. Doesn't quite make it. How about 20, 15, 15? No, no. 30? You know what you can do, actually? I know what to do. 2 raised to the 32nd minus 1. Oh no. 2 raised to the 31st minus 1. And then you take that log 5. Log, divide that by log 5. Alright, gives you 14. And I need 15 there. Take the same number. Take that log. 3. It's 20. And do that log 2. Same deal. $31. Are you ready? This should get everything. There you go. How's that? How do we do? A little faster. A little faster. Interesting. Now if we change these numbers a little bit, wrong answer, yeah, no, it's gotta be, okay. So, we just took every number, printed it out, printed all these combinations in between, even the combinations that we can't afford. Actually, you should do this. Go even faster. Go even faster. There you go. You can even do better than that. You can even do better than that. Alright, how about this one? This one's a little more, there we go, a little faster. It's got a little more of what you would call terminates early. So we don't mess around with all these extra parts. Alright, I think that's going to be it for me for the night. Oh man, I spent a lot of time on this one. I kind of want to read the discussion. I don't want to think about this one too much longer. This one was kind of painful. It's pretty much just a brute force solution. Yeah. That's really it. It's just really brute force solution. Print out a bunch of numbers, dump them into a list, sort the list, get the index of the one you want, call it a night. That's it. Let's see, what does the discussion say? DP solution, short explanation, detailed explanation, short ON, Python, C++. Mine is not O of N, not at all. Universal DP. Java, easy to understand. One pass, simple solution. I like Stefan's. Let's do the CPP one. Have an array K of first n ugly number. We only know at the beginning the first one, which is 1, then k of 1 equals the min of these 3. The answer is k0 times 2. So we move 2's pointer to 1, then we test k of 2. Min. So I want to be careful about the cases, such as 6, in which we need to forward both pointers of 2 and 3. Cases such as 6, which we need to forward both pointers of 2 and 3. Oh, really? Dynamic programming solution, huh? Okay, well, I guess I could have done it that way. Oh, I didn't think about that. Man, I'm so slow. I don't realize things sometimes, you know? Alright, I got it. I have an idea. Interesting. Thinking if I could do this recursively. Let me think about this. I should definitely go to bed, but let me just think here. I gotta really think about this. I want to use something recursive and then memoize it. However, this is a challenging question. I guess I'm thinking of a quadratic solution where you take a look at all of the previous solutions and you'd multiply by 2 or 3 or 5 and take the smallest of all of those numbers. It's kind of like a breadth first search. Just thinking here. Depth first search, breadth first search. Breadth first search doesn't seem very good. So these dynamic programming solutions, but I'm trying to figure out if there's a way to trying to figure out if there's a way to do this without a way to do this where I can memoize. So this is apparently correct. Very interesting solution. Okay, well. Alright, let's do it this way. I have an idea. It's gonna go like this. So here's one approach. I don't really need to say this, I think I remember the idea. Let's try a different approach. Let's do, we're going to use tuples. And A, B, and C as the parameters. Or we can use a tuple, yeah. Call it alpha. What we're gonna do is we're gonna have the solutions we're gonna have tuples of okay. Alright, that's a little confusing. We're gonna do it without memoization first. There's an analog between the tuple and n. That's kind of the, not n, but the value that we're looking for. This is kind of tricky. There's an index, there's a value, and then there's these three, I call them alpha parameters. I don't know what you want to call them. That's why I'm getting kind of tripped up, because it's kind of unusual. Just thinking how to appropriately approach this. Because you do memoize, forget the memoization for now. Let's just say, what are we trying to do? Well, there's a given n. And you say, so you can have both, well, yeah. Let's do it this way for now. What I want to say is, I have this val 1, val 2, val 3, right? We'll say if we don't really need to do this yet. A is greater than or equal to 1. Then we can consider or we'll just say new val. This is so confusing. I don't even know what I'm trying to do. I want to say something like, call this recursively 3 times. Each recursive call, you're going to get with, divide by 2, divide by 3, divide by 5, whatever your alpha value is. Call this recursively with those parameters changed in those ways. You get 3 different results. Whichever result gives you the smallest value. So we'll do R1. Something like this. In the case that these things are large enough. Something like this. this up later. It's going to handle the degenerate cases somehow. Do something like this. Just a little unusual. Let's see. So make these 3 recursive calls if they're possible. Let me take the best of those 3. Now, here's the tricky thing. We don't know where we should start with our alpha value. That's kind of the problem that I have, is this is like exploratory, it's not the other direction. In other words, really this should have an n, some value n, and we want to backtrack from n. There's some value less than n. If we multiply it by 2, we'll get the value we're looking for. Or if we multiply it by 3, or if we multiply it by 5. Yeah, I was of the opinion for a long time that most, if not all, of dynamic programming problems could be rewritten as memoization of recursive problems. But maybe I'm wrong about that. Because you don't necessarily know where to begin, I guess, something like that. In other words, finding this nth number, you don't know which number you're going to need. To get this number. You don't know how far back you need to go in your recursively. You could recurse on all of the smaller numbers, but that seems rather inefficient, doesn't it? So, I don't really know how to articulate it, but I guess it's not the case. It's not always the case that you can simply run a brute force solution and memorize it. Doesn't seem to always be true. Let me lay down for a minute or two. Let me just ponder this. Let me just ponder it. Man, every time I try one of these problems, it's a learning experience. It's a learning experience. Which is just good. It's healthy, but man, oh man, quite the learning experience indeed. Oh, my body. Oh. So the way the dynamic programming solution seems to be set up is that you really only have 3 numbers to consider, and you multiply them by 1 by 2, 1 by 3, and 1 by 5. And each of these 3 different numbers to consider, those are all, I guess, produced sort of by induction. I don't know, man. I want to say something like, sometimes you can't recurse in like a depth first search that you can memorize, because you can't do a depth first search to solve the problem. You can only do a breadth first search. Because technically this search space is like infinite. That's part of the problem. So it really is like a breadth first search. Sort of. I don't really know. I don't really know how to describe it. How to describe it. I don't know. I think the depth first search is, the recursion, not the recursion, the algorithm will say it's pretty simple. I think what it means is, you sort of have these alpha, you have these 3 parameters called alpha 1, alpha 2, and alpha 3, or just A, B, and C, right? There's exponents A, B, and C. And basically, excuse me, no, they're not, no, I take that back. They are not, they are not the, not the exponents. What they are is they are some number that when you multiply it by 2, some number smaller than the number, actually I guess they're potential numbers, where one of them is a potential number that you multiply by 2, another is that you multiply by 3, another you multiply by 5. And the smallest of those 3 numbers must be n. So these are all numbers that precede the nth number that you're looking for. The smallest of those 3. Excuse me, one of those 3, the smallest of those 3, is exactly the number that you're looking for. Yeah. And way that we generate those numbers is we start off initially, I guess, at 0 for all of those. So they all start off at 1, so you have 2, 3, and 5. We'll start off at 1, or you can use an index to represent these numbers. And what you do is you say, okay, our next value has got to be the minimum of those three numbers, right? 2 times the first, 3 times the second, and 5 times the third. And we would update each of these indices, each of these values. Now every one of these numbers, these 3 numbers, they're one of the ugly numbers. So when you update one of these ugly numbers, you don't multiply it just by 2. You actually update it to the next ugly number, up from where it was. If, for instance, 2 was the one that you selected, which is a little weird to think about, a little strange. But yeah, you'd have like you'd have these 3 different numbers, and whatever ugly number you multiply it by some value, and that gives you the next ugly number that you need. You would update, just update to the next ugly number. Does that make sense? I don't know. I'm not really used to writing dynamic programming solutions that don't have any kind of recursion. That's something that's kind of unusual to me. But it makes sense for this problem, I think. Because it's kind of a generative problem. It's not really like, you don't really know for the nth number, like, I guess it's kind of hard to figure out which number you're supposed to use to get that nth number. Which values you're supposed to manipulate to get that nth number. Because you have no idea what that number is. That's sort of the whole point. But you don't even know its relationship to the other numbers. Whatever it is, you can divide by 5, divide by 3, divide by 2. Obviously all of those are ugly numbers too, but it doesn't really help you, I guess. Because you don't know what those indices are either. Yeah, interesting. Yeah. So basically, you have three different choices: multiply by 2, multiply by 3, multiply by 5. For these values that are going to be ugly numbers themselves, so you're going to update them to the smallest possible ugly number that you know of at each point. That's pretty much it. So it's kind of this exploratory algorithm, I guess. But you start off at the first ugly number for all three options, and then that's the sort of the entry point, and then 2 times 1 is the next smallest. So you update that. Now it's a 2, that ugly number for that position. And then the next smallest would be 3, right? That 2 times 2 is 4, 3 times 1 is 3. You pick that one, 5 times 1 is still 5. Then you update that one to the next ugly number, which is 2. So you have 4, 6, and 5. Then you pick 5. Excuse me, you pick 4. Now you have 1, 2, 3. So that third number, or that 2 times 2 becomes 2 times 3. So you have a choice between 6. 6? You did 3 already, right? I guess it's 6, 6, and 5. That's kind of interesting. Is that right? You would do 2. You would do 2. So that goes to 4. 3. So that goes to 6. 4. I think that also goes to 6. Is that right? 5, which then goes to 10. 6, which goes to 8. I think you pick 6 again. And I'm not really sure how that works. But I think for the 6, you would I think for 6 you would still update it, but you wouldn't change the value again, if that makes sense. I guess if any of them are equal, you would just update it again from 6 to 9. Skip it, something like that. I'm not sure how that works. I have to take a look. See the dynamic programming solution, how that's handled. I think you handle it all. Actually, yeah, I think you handle the multiple, like if you have 6 and 6 twice, I think that gets handled both in the same step. Yeah, so it looks like basically you have the multiples of 2, multiples of 3, multiples of 5, and then the smallest possible ugly number that you could have to multiply by the next multiple. And that's the invariant as you go. That's it. And that's your dynamic programming solution. Super interesting, but yeah, it's linear with respect to the output, so it's very efficient. Very interesting. Very interesting. I would not have thought of that on my own. Absolutely not. I mean, now I have that available to me. The next time that I see a similar problem, although I'm not so sure I would even recognize it to apply it. But yeah, for something that's kind of, generative with regard to sequences, and there's sort of this, I guess, almost like multiple dimensions or something like that, then I guess you could apply a similar approach. Yeah, I wouldn't really know. This is a sort of a dynamic programming solution that I really wouldn't know how to apply recursion to. Let's call it ret. Start everything off at a 1. Or 0. 0 is fine. So we'll say for int 0. So we have int a. Oops, didn't mean to do that. And we're going to I think we can use this. Minecraft. Actually doesn't use, doesn't quite do what I think it does. Yeah. Well, that works. It's kind of funny, but yeah. Let me just look at that again. Okay. Need the right compiler for it, but it should work. You just say that's pretty much it. I think that's the whole algorithm, just like this. Super simple. A, B, and C. Start off at 0, set 0 to 1, I equal to 1, say all of these things, get these values, get the minimum, update I, 1, 2, whatever that value is. So in our case, it's n minus 1, but in our case it'll be 2, right? And we say, okay, if what you selected was 2, what you selected is related to A, increment A, it's related to B, increment B, it's related to C, increment C, and then update I. And we're going to go all the way to, I think actually equals n. Yeah. No, not equal to n. Just right below, right before n. Right before n. And that's it. I think that's it. See how we do. Yep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 100, 1,000, 1690. See how we do. Correct. Correctamundo. There you go. That's a lot faster than I had before. Yep. Super simple. Super succinct. Brother. I don't think that I would think of a problem like a solution like this again in the future. I don't think so. I don't think so. This was a very interesting solution. Very interesting problem, very interesting solution. I don't really know. It's like nothing like I've thought of before, nothing I've seen before. Or I shouldn't say thought of, nothing I've seen before. It's sort of one of those exploratory kind of questions where you generate a bunch of numbers. Really interesting, but definitely exceedingly challenging for me to do. I think I understand the solution now, though. I think I got it. I think I could solve a similar question in the future. It's just, yeah, that was very challenging. I'll give this question a +1. +1. Interestingly, some solutions were even faster. Kind of curious if there's a way I could make this even faster. Could probably do this. How about that? How about that? Is that better? That is better. It's better. Not creating the initializer list. Yeah, actually not even calling this function in the first place is even better. If you do okay, XYZ, you do no, I don't know if this is better. think it's a little faster if we do it this way. It's got some typos here. I don't know if that's much faster, it might be. No, not much. It's fast, but not really faster. Pretty good. Yeah, okay. Well, anyway. It's definitely, for readability's sake, it's probably better to do it this way. Oh wow, nice, 4 milliseconds, sweet, awesome. Some people had 0 milliseconds, which is pretty wild. Not sure exactly how they did that. Yeah, how did they do that? How did they do that? How did they do that? Oh, okay. Yeah, alright, okay, anyway. Sweet. GG. So, yeah, thank you all for watching, hanging out, saying hello. Do appreciate it. Talk to you all soon. Man, spent a lot of time on this problem. This is a hard one, man. I really struggle with this. Pretty interesting that you could brute force it. Just like, you know, generate a whole bunch of these numbers and then sort them. Unfortunate that my rule generating rule idea didn't really work. That's kind of unfortunate. And then the other brute force solution was pretty interesting. Got pretty far with that. Just, you know, somewhat dynamic programming, but the difference is that this sort of jumps ahead the right amount, whereas that other approach doesn't really jump properly. You know, it just kind of try to, brute force iteratively search as many numbers as we can. But this is pretty neat. I like this solution a lot. This is really clever. It's very clever. I have to remember this for the future for similar kinds of problems. I don't know if I'll see a similar one again, but very neat, very succinct, very interesting. I learned something new. Alright, I'm gonna go. Thank you again for watching, hanging out, saying hello. I do appreciate it. Talk to you all soon. Have a good rest of your night. If you like the stream, don't forget to subscribe. I don't know how much longer I'll be streaming on YouTube. I don't know, man. Like, I don't really have a home anywhere else right now, so YouTube it is for the time being. I don't really like the other services out there. They're all like kind of crummy. Don't really have very good video sharing platforms out there or live stream platforms. So anyway, take care. Take care.